Hello guys, welcome back to my channel. In this video, we are going to look fully into erythropoiesis. So by way of definition, erythropoiesis is just the production of red blood cells. So and in erythropoiesis, that is the definition, production of red blood cells. Then we also need to talk about the sites of production, the genesis of production, okay, and also the regulations. Regulation in terms of role of erythropoietin in the production of red blood cells, regulation in terms of the nutritional requirement for erythropoiesis, which is a folic acid and vitamin B12. Okay, so we also need to look into iron metabolism. The iron is also one of the nutritional requirements. Iron metabolism, and we also need to look into formation of hemoglobin. How is hemoglobin formed? Of which we have discussed a little part of it in our previous episode. So starting with the definition of erythropoiesis, which is basically from the word erythro. So erythro means red. So cyte means cell. Erythrocyte, red blood cells. So erythropoiesis is just the production of red blood cells. So this production, though, if you are to complete your definition and say it's the production of red blood cells from the bone marrow, that definition might not be totally correct, okay? Because there are other sites where there could be production of red blood cells depending on the age, okay? So it is essential for you to know that production of erythropoiesis actually start from embryonic stage. So in the embryonic phase, so the stage of the embryonic phase is actually from week 1 to 3. So starting from week 4 down to start down to week 8, that is the period of organogenesis. Then we also have the fetal period. So at the early weeks of development, so red blood cells are being produced from the yolk sac. Okay, you all know your yolk sac from embryology. So that is the first site for red blood cell production. So now down to the middle trimester. So normally pregnancy is split into 3 trimester. There is the first trimester, second trimester, and third trimester. So the first 3 months is regarded as the first trimester. The subsequent 3 months from month 3 to the 6th month is referred to as the second trimester or the middle trimester. Then down to the third or the last trimester, which is from 6th month to the 9th month. So looking at this at the early weeks, so red blood cells is produced. They are produced in the yolk sac. So at the middle of trimester, so the liver, the spleen, and the lymph nodes, they come into the picture. So they also start producing red blood cells at the mid of the trimester, around month 3 to month 6 of intrauterine life. So now at the later end of the gestation, let's say the 8th month, the 9th month, and shortly after birth, and also after birth, so the bone marrow takes over from the spleen, from the liver, and from the lymph nodes. So the bone marrow takes over, and the bone marrow becomes the chief producer of red blood cells. So we all know the bone marrow is inside the bone. Okay, the bone marrow is just that structure that is inside the bone. That is inside the bone. So we have the cortical part of the bone. So at the center of the bone, there is a bone marrow. And this bone marrow is not limited to the long bones, because if you are talking about bone marrow, someone might be thinking it's only the long bones, which are the femur, the humerus, the long bones, are the femur, the humerus, the tibia, the fibula, the radius, the ulna. No. So even the membranous bone, which are the membranous of the flat bones, which are the ribs, the vertebrae, the scapula, the vertebrae, the scapula, the skull. So they also have a bone marrow. So at the last month of gestation and shortly after birth, red blood cells are exclusively produced in the bone marrow. So right from after birth till up to age of 5, so the bone marrow of all bones either long bones, which I've described earlier, long bones, which are the humerus, the femur, the tibia, the fibula, the radius, the ulna. Just mention it, the long bones in the body. So, and also the membranous bone, okay, which are the because that is kind of morphology of bone. So in terms of morphology, bones could either be membranous or the flat bones, or could either be flat or membranous and long bones. So up to the age of 5, from last month of gestation after birth till the age of 5, red blood cells are being produced from the bone marrow of all bones. Okay, either long bones, either membranous or flat bones. But it is essential for you to know that from age 5 to age 20, there's fatty infiltration. So fatty tissue, fatty substance infiltrate marrow of long bones. So and in that very case, what do you expect? So the marrow of long bones loses their erythropoietic function, and you are only left with the membranous or the flat bones to start producing to continue, because they are also producing right from the birth to age 5 together with the long bones. But what happened to the long bones, the pathology is not really the pathology. The changes that happened, okay, which is fat infiltration of the marrow of long bones. So they stopped producing. Meanwhile, membranous bone continues to produce even right after the long bones have stopped functioning, the membranous or the flat bones continues to function. So, and I told us the example of membranous bone are the ribs, the sternum, the vertebrae, the ilium, okay? So the ilium is the pelvic, it forms the pelvic bone, okay? So they start producing red blood cells. But then it should also be noted that even this membranous bone, as an individual aged, so normal aging process also occurs to the marrow of membranous bone. So normal aging process also happens. So as an individual aged, this membranous bone as well become infiltrated with fatty tissue, fatty substance, and depend on aging. So the level of the erythropoietic capacity of the membranous bone as an individual age also declines. So that is just that's part of the normal aging process. So that also declined. So and you should also note that anything that can affect the bone marrow, such as radiations can affect the bone marrow, or some drugs. So when you use some drugs like barbiturate and some other drugs that can affect the bone marrow. So all these things can have great impact on the erythropoietic capacity of the bone marrow. Now let's look at the genesis of our blood cells. So the genesis is just how the red blood cells are being formed from the stem cells down to the matured erythrocyte. Because the reason why I say matured erythrocyte is that there are some erythrocyte red blood cells, well, let's call them red blood cells, that they are not really matured. Reticulocyte cannot be called a matured red blood cell. So I'll be pointing out the differences shortly. So that stages of development, that stages, phases of changes that happened right from the stem cells down to the mature erythrocyte. Those are the stages of differentiations, and they constitute the genesis of our blood cells. So your genesis is just the source. Where is the red blood cell? Where is it coming from? Okay. So, and when we say stem cells, so especially from this word pluripotential hematopoietic stem cells, you should actually know that stem cells, there are different types of stem cell. Stem cell could be multipotential stem cell, pluripotential stem cell, totipotent stem cell. But in this regard, we are talking about pluripotential stem cell. This is a stem cell that is not yet committed to a particular cell line. So pluripotential hematopoietic stem cell could be either be committed to the uh, red blood cell line, erythropoietic line, or it could be committed to the lymphoid stem cell line to produce lymphocyte, or it will be committed to the monocyte line to produce a monocyte, or it will be committed to the granulocyte lines to produce the granulocyte, which are the neutrophils, the eosinophils, the basophils. Okay, So that is why it is called pluripotential hematopoietic stem cell, because it is not yet committed to a particular cell line. So now, from pluripotential hematopoietic stem cells, it becomes committed to form colony forming unit erythrocyte (CFUE). So now these are the stages that we have. So from pluripotential hematopoietic stem cells, it becomes committed to form colony forming unit erythroblast. From there, we have the proerythroblast. So from proerythroblast, several changes happens. So as I've told us, the red blood cell does not have nucleus. But right from the start, okay, right from the start, right from all the from the proerythroblast, the early normoblast, okay, these cells they undergo series of changes, and all these cells, the initial cells, they are cells that has they are cells that have nucleus, okay, they have nucleus. So there are changes that happen in which after some time. Now let's go to our whiteboard and see what we can do. So let's assume this is a blast cell, so with nucleus. So meanwhile, I told us that a mature red blood cell, from the morphology that we did, that's why we firstly did the lecture on our morphology of our red blood cells. If you have not watched that, the link to the video is in the description button. Kindly click the link and check. So now, for red, I say a matured red blood cell, a mature red blood cell should have hemoglobin inside it, cytoplasmic enzymes, okay, enzymes, then no nucleus. There is no nucleus, and this has nucleus. So a major changes that happens in this is that as the cell courses through the different stages, so there will be gradual reduction in the nucleus, which will eventually culminate into eventual absorption of the nucleus and other, and other organelles. Okay, and there will be gradual increase in the number of our hemoglobin, gradual increase in number of our hemoglobin, gradual increase in the number of our hemoglobin. So by the time you have a poor erythroblast, uh, the nucleus is obvious. Okay, the nucleus is still large. So after a successive stages of differentiations, the nucleus starts decreasing and the hemoglobin level start increasing. So those are the two major changes that is happening in our erythropoiesis. So now you can make your right guess and say that poor erythroblast is likely to have, because since it's the first, it's one of the first line of it's one of the first stage. It's one of the earlier stages of erythropoiesis. You can make your right guess and say that at that particular stage, the nucleus is still prominent and the hemoglobin is absent or is very low. Okay. So now, by the time you are now getting to your late normoblast, so late normoblast is also one of the later stages. You can make your right guess and say that okay, well, at late normoblast, the nucleus has become lesser. The nucleus has become smaller in size, and the hemoglobin concentration inside the red blood cell has increased. Okay, so those are the basic changes. I know that all these are nucleus, all these are hemoglobin is a protein on its own. So and that will affect the way the way the stages of red blood cells tends to die. Okay, it tends to die. So you can define this successive staging based on the disappearance of the nucleus one, the appearance of the hemoglobin two. And I said hemoglobin is a protein, so it will impact the way it tends to die. So it's more of acidic, it's either the dye could either be acidic dye or the basic dye. Okay, acidic dye or basic dye. So and also the staining. So those are the three parameters that you can use to to talk on stages of erythropoiesis, the stages of differentiation. Once again, the nucleus content, hemoglobin content, and the staining property. The staining property could either be with the acidic dye or basic die. So all these things you don't need to cram, you don't need to memorize much, and just know the basic principles, that is necessary for all this. So, and I said the early nomoblast, it contains the nucleus and lesser hemoglobin. So in that very case, it will stain with basic dye. Okay, it will stain with what? Basic dye. But by the time the nucleus has become smaller and the hemoglobin is now prominent, it's going to stain with acidic dye. So when you are being asked your multiple choice questions, this kind of questions that which of the following stains with your basic dye, and they say late nomoblast, intermediate nomoblast, just know that the basic dye is actually due to the higher concentration of the nucleus and the lower hemoglobin, while the acidic dye is due to higher hemoglobin and lower concentration of the nucleus, okay, or even absent nucleus. So having that basic principle in mind, you should be able to pick your answer correctly. Okay. So, and I've told us that the earlier the stages, the more the nucleus, the lesser the hemoglobin, and the staining property is going to be basic dye. And the later the staging, okay, the more the hemoglobin, the lesser the nucleus, and the more acidic the dye is going to be. So let's quickly give you a run through of all the stages that we have here. So there's the pro-erythroblast, there's an early nomoblast or basophilic erythroblast. So there's intermediate nomoblast or polychromatic erythroblast. Okay, then there's late nomoblast or autochromatic erythroblast. So I've told us the nucleus, in terms of the nucleus, in terms of the hemoglobin concentration, and in terms of the staining property. So now reticulocyte, okay. So reticulocyte has enough hemoglobin, the nucleus and some of the organelles are already absorbed or extruded. So the moment erythropoiesis occurs in the bone marrow, the bone marrow have been supplied with blood vessels, and you know that when you are talking of tissue, bone marrow is a tissue. So the blood vessels that come in contact with tissue is the capillaries. So the blood cells that are released, that is actually released into the blood capillaries, is the reticulocyte. Okay. So after some 1 to 2 days, which is about 24 to 48 hours, so the reticulocyte becomes, it becomes adult, it becomes mature erythrocyte. Okay. So, and that's why at any point in time, the reticulocyte count, it also matters. Okay. So the reticulocyte count, there's a mature erythrocyte count, and there's a reticulocyte count. So the reticulocyte is actually a pointer to to formation of our new red blood cells. Okay. So now I said, now just now that we have talked on bone marrow producing red blood cells, how is this production? How is it being regulated? This is also very important because in our body system, regulation is very, very important. So, and that's why even that's why at any point in time in physiology, you always be talking of homeostasis. So, homeostasis is just the maintenance of the fairly constant internal environment despite changes in the external condition. So, how is this regulation? How is being maintained? I say the normal concentration of red blood cells, just as I've earlier pointed out in our in the morphology video that we did. So if you have not watched that, the link to that is in description button, description. So you click on the link and try to watch. So, and also don't forget to subscribe and like this video. Thank you. So for erythropoietin, what erythropoietin actually does is that it stimulates red blood cell production in response to hypoxia. Okay, so let's go to our whiteboard. So erythropoietin, okay, erythropoietin, hypoxia, red blood cells. Now, what is the relation that occurs? Excuse me. What is the relation that occurs between them? You know that I told you that the chief function of our erythrocyte is to transport our hemoglobin, and by transporting hemoglobin, it's actually transporting oxygen. So, in any time when there's hypoxia in tissue, okay, when there's cellular hypoxia, so there's low oxygen transport or there's low oxygen supply to the tissue. So, and this could be due to so many factors. It could be due to that the tissue are under perfused, so the tissue are not being perfused very well, or it could be as a result of the issue from the lungs. Perhaps maybe the oxygen intake is not enough. maybe due to pulmonary diseases, okay, or maybe due to loss of blood, and in that very case, the tissues are not being perfused, or hypoxia due to maybe the diameter of blood vessels has increased, widespread vasodilation, and as a result, there's under-perfusion of blood to the tissue. So whenever there's hypoxia, so and you all know that the kidney is also perfused by blood. So about 25% of cardiac output goes to the kidney. So when the kidney too is not getting enough blood enough, and when they say enough blood, you know that for blood you are going to get blood cells, hemoglobin, oxygen. So when it's not being perfused with enough blood or enough oxygen, enough hemoglobin, the resultant effect of that is that the kidney will be stimulated to produce uh there will be genetic induction of you know hypoxia inducible factor, HIF, hypoxia inducible factor, which will then cause erythropoietin secretion. So erythropoietin is produced mainly in the kidney in response to hypoxia. But then there are other non-renal sensor of erythropoietin. Okay, such the liver as well can also produce a little quantity of erythropoietin. Okay, the liver can as well produce a little quantity of erythropoietin. So hypoxia inducible factor (HIF) induces erythropoietin gene transcription. From there's production of erythropoietin. Now, what does erythropoietin do specifically? So the erythropoietin does not, I said we have the pro-erythroblast, from there the early nomoblast, intermediate nomoblast, late nomoblast, then reticulocyte, and matured erythrocyte. But what the erythropoietin does is that it actually acts on the earlier stages. Okay, it acts on the earlier stages such as the pro-erythroblast, and also accelerate the timing of from pro-erythroblast to matured erythrocyte. It accelerates the timing so that by the time the pro-erythroblasts are being formed, it will only take lesser time before they get to the stage of a mature erythrocyte. And in that very case, more red blood cells are being produced in the blood. And you know that when there's more red blood cells, there's more hemoglobin, and of course, there will be more oxygen. So, and that is a way to correct the low oxygen in the tissue, hypoxia. So that's just a basic explanation for it. Now let's go back to our slide and see what we can do. So erythropoietin stimulates red blood cell production in response to hypoxia, and it is mainly produced in the kidney, just as I've rightly pointed out, while some are produced in the liver. So hypoxia inducible factor 1 in kidney induces erythropoietin gene transcription. Non-renal sensors may also stimulate erythropoietin production. And the effect is that the moment hypoxia begins, the kidney sense that, oh, there's low oxygen tension, because the kidney itself might not be getting enough oxygen, and the kidney sense that, there are different structures in the kidney, the messengers of the kidney, when you talk of the cortex, you talk of the medulla, then the interstitial space. The interstitial space in the kidney is known as the mesengium. Okay, so the erythropoietin in some text they will say is produced from the mesangial of the kidney, but based on your level, it's just enough to say that erythropoietin comes from the kidney. That is enough. You don't really need to be so much specific about that. So erythropoietin is being produced, and erythropoietin immediately begins action. So and maximum production of red blood cell is being reached within 24 hours. So maximum production of erythropoietin is being reached within 24 hours, and new red blood cells appear after 5 days. Okay, so as I've said, the stimulation is actually from the earlier stages of differentiation, which are the proerythroblast, and then accelerate that process. So the stimulation is on the proerythroblast production and speeds up till the what? And speeds up the early nomoblast, late nomoblast. So it's not as if it is stimulating the early nomoblast, late nomoblast. The stimulation comes from the proerythroblast, and then new red blood cells appear after 5 days. So you can see that there's a short time between poor erythroblast and mature red blood cells. So new red blood cells appear after 5 days. So in all of this, for your synthesis of red blood cells, I told us earlier that there is a need for a nutritional requirement, okay, which is the iron and the vitamin B12 and the folic acid. So in our subsequent videos, you try and discuss more about this. So make sure you subscribe, you like our channel. If you have any comment, my Gmail is open. So I will be expecting our comment, our clarifications. Thank you very much for staying to the end of this video. See you again.